Extra, extra, read all about it.
If you're thinking this is going to be just yet another workbench narration, well, you might want to wait until you've seen me pass 1,000 volts through my body and then make up your mind. Since I've started working with the electronics and building little IoT devices, I've become concerned about touching electronics and potentially frying them or otherwise causing damage to them. And for that reason, I've become interested in ESD gloves. Let me clean up some of this mess here. This is horrible. The gloves, I want to wear gloves because, well, first of all, the oil from your hands will cause damage to the enamel that's coats circuit boards and PCBs and other electronic components. And we don't want to do that. And also, well, you've done it. You've rubbed your feet on a carpet and stuck your finger out to a friend and zap! All of a sudden, you've given them a shock of somewhere between 3,000 and 30,000 volts. Well, imagine if you do that to something electronic. You're going to fry it or at least shorten its life. We don't want to do that. So I became interested in the qualities of anti-static or electrostatic discharge-safe gloves. Gloves that will either not build up static or that will slowly dissipate any static charge that you might build up on your body. Well, there are a lot of different gloves that you can use. You can wear latex gloves, and those are not necessarily good. I'll show you why. And then we've got cloth gloves with coatings of different kinds, and nitrile gloves. There are a lot of different gloves to choose from, and, well, I didn't know which kind were any good, so I bought a bunch of them, and I wanted to test them. That's what this next series of videos is going to be about. Now, when you're working with electronics, everybody knows you want to be grounded. Now, I know a lot of computer repair guys, and I'm guilty of this myself, have never worn a wrist strap when they're working on electronics, when they're working on their computers. I've swapped out memory chips, I've replaced CPUs, I've done all sorts of work on computers without being grounded. But at the same time, I've touched the case of the computer that I've been working on to make sure that, well, I'm at the same electrical potential as the components in the computer are. And when I do that, well, there's not going to be any static charge passed between me and the computer because we're at the same electrical potential. Static discharge happens when there's a different electrical potential between you and whatever it is you're about to touch. And a lot of times, well, when you zap somebody, that's a pretty high voltage. If you do that to electronics, you're going to damage them. So what you want to do is you want to be grounded, or at least have the same electrical potential as whatever it is that you're going to be working on. Right now, this steel bar and I are at the same electrical potential because we're connected. So, if this is connected to my wrist, I can pick it up and I know I'm not going to zap it. The problem could come in when I first make this connection, though, because this is attached to my wrist and this is not. So if this has a different charge relative to me and I touch it, well, I could fry it. Want to always be careful about that. So I have a grounded work area here, and I also have this common connection to whatever electronics I'm working on. Now, most of the time, this isn't practical. Where am I going to clip on this WeMOS D1 board? There's no place to do that. I just have to keep this thing in a safe work area and make sure that if I do build up a charge, it's going to be dissipated relatively quickly, and hope that this thing doesn't have a different charge. So the gloves that I wear, I don't want them to be perfectly insulative, because if they are, they could build up a charge, or I could build up a charge, and that's different from whatever electronic component I'm working on. I want the gloves to conduct whatever charge I might build up to ground. And that way, I'm less likely to damage any electronics that I'm working on. We're going to play a little bit here. Oh, incidentally, these wrist straps don't immediately conduct whatever charge you build up to ground. They have a 1 megohm resistor in them, so they discharge it fairly slowly, but not so slowly that there's a risk that you might pass that charge on to any electronic components. For instance, hard drive manufacturers say that ideally they want to dissipate any charge from their workers within 5 seconds, less than 5 seconds, and ideally for very sensitive electronic devices, and there are some components of hard drives that are extremely sensitive to static. They want their workers to discharge any charge they might build up in less than 2 seconds. So a 1 megohm resistor is going to pass a charge not so rapidly that you'll feel a painful shock when you do it, like when you zap a friend who may not be your friend for much longer, but it will dissipate that charge slowly enough so as not to cause any damage to you or to the components. Now, to perform this test, I've got this megohm meter right here. And the megohm meter generates either 5 volts and will measure up to 200 ohms, or 500 volts and measure up to 100 megohms, or it'll generate 1000 volts and measure up to 500 megohms. 0 ohms on the higher scales, infinite resistance up here. On the lower scale, 0 ohms and 200 ohms. Now, I'm going to charge myself with 1000 volts. You're going to see that. And hopefully I'll live through it. If not, well, when you watch this video, you're going to see something you don't expect. But, well, we'll find out what happens. And why whatever happens. And I'm going to use some homemade equipment here for my test. Now, the people that do these tests in industry for the different gloves, they have some very specialized equipment and some very exacting standards. But the standards I've seen just don't seem very clear to me. There are a lot of different standards. Some of the standards say, well, you want to be between, you want the gloves you're testing to have a surface resistance or an in-use resistance or whatever of between 100,000 ohms and 1 billion ohms. Others I've seen say you want a resistance between 1 megohm and 25 megohms. I think that's probably safe for the tests that I want to do. If I can find a glove that has a reasonable resistance, will dissipate a charge, and not shock me, and will protect the components that I'm working with, then that's what I'm going to go with. I just don't know how these different kinds of gloves perform. So that's what we're going to find out. And one of the first tests we're going to do is on gloves that I've read are an absolute no-no. Latex gloves. Latex gloves, you'd think, are perfectly insulative. They'll protect you from any electricity passing through them, or and keep your hands clean. Well, there's something to that. When you're working with germs and so forth, you want a glove that's going to keep the germs off. When you're working with toxic chemicals, you don't want those getting on your skin and so forth. But these latex gloves, well, they behave a little bit differently from what you might think. We're going to measure the resistance of these gloves in two different ways. One, we're going to measure the surface resistance of them when I'm not wearing them, and then we'll measure the resistance through the glove when I am wearing them. And you're going to see it's kind of a different result than you might expect. This little Ohm Meter right here, very interesting device, is very useful for you for work out in the field. It's got a generator built into it. Turn this crank right here, and you see right now it's got zero resistance, or infinite resistance. That's at 1,000 volts. This is on the 5-volt scale, zero resistance, or infinite resistance. And it's generating a DC current. And the reason we're getting infinite resistance is because the leads aren't connected. But if I connect these leads, well, we've got, it looks like about 20.2 ohms, 0.1 and 0.2 ohms resistance in the lead here. At 1,000 volts, well, resistance is practically zero for all intents and purposes. Now, just to prove to you that this is actually generating 1,000 volts, break out our trusty fluke, connect the leads, and on the 1,000 volt scale, it's generating 960 volts. Now there's a resistance in this circuit of about 10 megohms on the 1,000 volt scale here on the bottom, about 10 megohms. On the 500 volt, or on the 100 megohm scale, generating 500 volts, let's see what it does, generates, about 525, 526 volts, and we've got a resistance in the circuit of about 10 megohms. On the lowest scale, we're generating about 5 volts, and the resistance is, well, through the roof here, because it's still going to be about 10 megohms. That scale only measures up to 200 ohms. So, let's see what kind of current, or what kind of voltage will pass through these latex gloves. First we'll just start at 1,000 volts right there. And, well, they've got practically infinite resistance. It's not actually infinite resistance, because at 1,000 volts, according to this meter, there's about 500 megohms of resistance in there. In other words, these leads are about a 1/4 inch apart on the surface of these latex gloves, And over that distance on these latex gloves, there is a charge passing from one lead to the other with a resistance of about 500 megohms. Now, when I put this glove on, it's going to be a lot less. And here's where it starts to get interesting, because the wrist strap I'm going to use is not one with a 1 megohm resistor in it. It's one that I made out of, well, some of the most useful materials on the planet: aluminum foil, duct tape, Velcro, a little bit of copper wire, and an alligator clip. So I'll put this on. And I'll clip myself to this steel bar here. Now, this isn't a regulation steel bar used for testing. Or, no, I don't want to clip this to the steel bar. The handheld bars that the professionals use when they're testing are stainless steel. They've got a polished surface. They're very low resistance. But this is the best thing I've got, and it's good enough for what I want to do. So I'm going to plug the ground, or the negative side of this generator, into my wrist strap. And I've got the positive side connected to this iron bar. And, well, first I'm going to find out what my resistance is in this circuit, wearing latex gloves at 5 volts. Well, the resistance is practically infinite. It's way off the scale there. At 500 volts, it's going to be a little bit different, though. At 500 volts, it's passing through my hand, and I can feel it in my wrist. The resistance of this circuit, which has me in it, is about 5 megohms at 500 volts. And at 1,000 volts, okay, if something happens, call 911, okay? Here goes. At 1,000 volts, the resistance in this circuit is about 2 megohms. And I felt that in my wrist. Now, the reason it's so much less is because we're not going across the surface of the glove, but we're going from one side of the glove to the other, and you can already see that there's sweat building up on my hand right here. So these gloves are not perfectly insulative, but they do have a sufficient resistance that, as long as I'm grounded or connected to whatever components I'm working on, we'll have a common electrical potential, and I won't pass any static electricity onto them. Now, the problem with latex gloves is, first, a lot of people are allergic to them. Second, they're uncomfortable because, well, you start to sweat in them, and that's never fun. Third, you can build up a charge on the surface of them. You got to be careful with them. And they've got some other properties that just make them unsuitable for work with electronics. So, we're going to test some of these other gloves and find out what their electrical properties are. So, if you want to see more, come back for part 2. Thanks for watching.